Welcome back for another deep dive. And today we're going to be looking at something that might seem pretty basic at first glance, but it's actually full of little quirks and nuances.
Yeah, it's one of those things, you learn about early on in your programming journey, but maybe you never really have to dig into the details of how it all works.
Right. And today we're talking about floating-point arithmetic.
Exactly. And even if you've been coding for a while, I think you'll find some interesting stuff here.
Yeah, definitely. So let's set the stage here. I think most of us kind of have this idea that floating point is all about representing real numbers, like with decimals.
Right, using a limited number of bits.
But how does that actually work in practice?
Yeah, so it's like you're trying to fit this infinite world of real numbers into like this tiny, finite box of a computer's memory.
That's a good way to put it.
You need a system to like approximate those numbers, and that's what floating point representation does.
Okay, so walk me through that system. What's going on under the hood?
Well, first you got to remember that computers think in binary.
Right, base 2.
While we humans are used to decimal base 10, so at its core floating point is expressing a number using a base, a significand, and an exponent.
So kind of like scientific notation.
Yes, exactly, like scientific notation.
Where you have that like really big or really small number and you multiply it by 10 raised to some power?
Yeah, and with floating point, it's the same idea, except we're using 2 as the base.
Okay, I'm following you.
And you can actually see this all laid out nice and neat in equation 1 in Appendix D.
So does that mean like all the limitations of floating point come down to like just having a fixed number of decimal places?
Well, it's not quite as simple as that. It's not just about a fixed number of decimal places. The real issue is that fundamental difference between binary and decimal.
Oh, okay.
Because some numbers that are like really easy to represent in decimal,
They become like repeating forever fractions in binary.
infinitely repeating fractions. Exactly.
So can you give me an example of that?
Yeah, absolutely. Let's take a look at the number 0.1.
Point 1. Seems simple enough?
Right. Seems totally straightforward in decimal.
Uh-huh.
But when you convert that to binary, it becomes an infinitely repeating fraction.
So even something as basic as point 1 can't be precisely represented in binary.
Exactly.
What are the implications of that for us as programmers?
Well, it means that whenever you're working with floating point numbers in your code, you're always dealing with approximations.
Ah, I see.
And those approximations can lead to some unexpected behavior if you're not careful.
So I guess rounding errors are a big one.
Rounding errors are definitely part of it, but it's the way that floating point precision wobbles that makes things even more interesting.
Wobbles. Okay, now you got to explain that one. What do you mean by wobbles?
So imagine like a ruler, but the markings on the ruler are getting farther apart as you move away from 0.
Okay, I'm picturing it.
So that's kind of what happens with floating point numbers. The distance between representable numbers, what we call oaks or units in the last place, increases as the magnitude of the number grows.
So like a fixed error in terms of those ULPs, it could have different effects depending on like where you are on the number line.
Exactly, and that's why we often talk about relative error when we're thinking about floating point, not just the absolute error.
Okay, so can you give me like a concrete example of how this wobble factor actually plays out in practice?
Sure, so let's take the number 12.35 as an example. If we're storing that number with a certain precision and we have an error of 1 oak, that 1 oak represents a certain amount of like absolute error. But now let's say we have the number 1.24 times 10 to the 1.
Okay.
Which is basically the same number but expressed in a different way. That same 1 ULP error is going to translate to a different absolute error. It'll actually be 10 times smaller.
Wow. So it's not just about how many decimal places we can store, it's also about the magnitude of the number itself.
Yeah, exactly. And this concept is really tied to something called machine epsilon, sometimes just called epsilon. It's basically a measure of that wobble factor. It tells us how much relative error we can expect in our calculations.
Okay, so this is really making me think about calculations in a new way. Are there any situations where these quirks of floating point become like especially problematic?
Oh yeah, definitely. One really common scenario is when you're dealing with subtractions, and specifically when you're subtracting numbers that are very close to each other.
Okay, what happens then? Does it just make the rounding errors worse?
It can be much worse than that, actually. It can lead to something called catastrophic cancellation. And it's a pretty dramatic name, but it really does describe what can happen.
Okay, I'm officially intrigued. So tell me more about catastrophic cancellation and how do we avoid it?
So you've got these two numbers, right? And they're almost equal, but they both have these tiny little rounding errors from like previous calculations.
Uh-huh.
And when you subtract them, what you're left with is mostly just those errors all amplified, not the actual difference you were trying to find.
So it's like those rounding errors were hiding there all along and then the subtraction just kind of blew them up.
Exactly. It's like they were lurking in the shadows, waiting to pounce.
Oh, that's kind of creepy when you put it that way.
Yeah, well, floating point can be like that sometimes, full of surprises.
Okay, so can you give me a real-world example of this catastrophic cancellation thing?
Sure. Imagine you have b equals 3.34, a equals 1.22, and c equals 2.28.
Okay.
And you want to calculate b squared minus 4ac.
Yeah, I remember that from algebra.
Right, it's the quadratic formula. So if each of those intermediate calculations is rounded to the nearest floating point number, b squared ends up being 11.2 and 4ac rounds to 11.1.
So far, so good. They seem pretty close to the actual values.
Well, but here's the thing. When you subtract 11.2 and 11.1, you get 0.1. But if you calculate b squared minus 4ac with like full precision, the real answer is 0.0292.
Whoa, that's a huge difference.
Right, and it all happened because those tiny rounding errors got magnified by that subtraction.
So this is making me a little nervous about all the subtractions I've done in my code.
Yeah, I mean, it's definitely something to be aware of, but don't worry, there are ways to protect yourself from this kind of catastrophic cancellation.
Okay, good. Because I was starting to think I should just never subtract anything ever again.
Haha, no, you don't have to go that far. One really simple but effective technique is to use a guard digit.
A guard digit. Okay, what is that?
So basically, it's like an extra digit that gets used internally during calculations, especially during subtractions, and it acts like a buffer to prevent the loss of significant digits during those intermediate steps.
So it's like having an extra layer of precision to protect us from those rounding errors.
Exactly. It's like a safety net for your calculations.
Okay. I like it. Do you give me an example of how that works in practice?
Sure. Let's go back to subtracting those two numbers that are really close together. Say x equals 1.01 times 10 to the 1, and y equals 0.99 times 10 to the 1.
Okay.
Without a guard digit, their difference would be 0.02 times 10 to the 1.
Okay.
But the correct answer is actually 0.17.
Wow, that's more than 8 times bigger.
Yeah. But with a guard digit, the smaller number, y, is temporarily truncated to 4 digits before the subtraction happens. And that preserves those crucial leading digits and gives you a much more accurate result. In fact, there's actually a theorem that proves this. Theorem 9 says that using a guard digit helps to bound the relative error in subtraction.
So even though it's just one tiny little digit, it can make a huge difference.
Absolutely. It's one of those small details that can have a big impact on your results.
You know, this all makes me wonder, is there any way to totally eliminate rounding errors in floating point? Is there a perfect system out there?
That's a great question, and it brings us to the concept of exact rounding.
Okay, tell me more.
So exact rounding is the ideal scenario. It's where every floating point operation is calculated as if you had infinite precision.
Wow.
And then the result is rounded to the nearest representable floating point number.
So why don't we just always use exact rounding? Is it too computationally expensive or something?
Well, it has a lot of advantages. It makes software more portable, and it simplifies how we think about floating point. But unfortunately, it's not always feasible, especially when you're dealing with transcendental functions.
Transcendental functions like sine, cosine, exponential functions, that kind of thing.
Exactly, because those functions involve infinite series. So you're kind of always going to have to round at some point.
Yeah, that makes sense. It's like you'd need infinite time and resources to calculate those things perfectly.
Right, and this actually leads to something called the table maker's dilemma. Let's say you're trying to calculate x 0.626 to 4 decimal places, and your super precise calculation gives you 5.0835.
Okay.
How do you know whether to round that up or down without knowing what the value is to even more decimal places? You could end up having to calculate it to a ridiculously high precision just to get the rounding right.
So even in a perfect world, exact rounding can be tricky. I guess we have to accept that we're dealing with approximations in floating point. But you mentioned earlier that the IEEE 754 standard has some other tricks up its sleeve, like hidden features.
Oh, yeah, for sure. Remember when we talked about the smallest representable number? What would you say is the smallest number you can represent in floating point?
Well, based on what we discussed so far, I'd say it's determined by the smallest possible exponent and a significand of all zeros.
That's a good guess. But it's not the whole story. There's this whole other category of numbers called denormalized numbers.
Denormalized numbers. Okay, now you've really piqued my curiosity.
Yeah, they're kind of like these secret bonus levels in a video game. Most people don't even know they exist.
I love that analogy.
So these denormalized numbers, they live in that space between 0 and the smallest normalized number. They're like filling in the gaps.
So they're like the missing pieces of the puzzle.
Exactly. And they bring this extra layer of nuance to floating point, just like those bonus levels add complexity to the game.
So how do these denormalized numbers actually work? Do they break the rules of how floating point numbers are usually represented?
They kind of bend the rules a little bit. So usually with normalized numbers, the leading digit of the significand is always a 1.
Right.
But with denormalized numbers, we relax that rule a bit. and we allow it to be a 0.
Oh, interesting.
And this lets us represent even smaller values, so you get this nice smooth transition as you approach 0.
So instead of just like dropping off a cliff at 0, there's this gentle slope of denormalized numbers leading down.
Yeah, exactly. It's called gradual underflow, and it helps make calculations with really tiny numbers more predictable.
Okay, so it's like a safety net for those edge cases where you're dealing with really small values.
Exactly. So you don't have to worry about things just suddenly dropping to 0 when they shouldn't.
I like it. It seems like the folks who designed the I-754 standard really thought of everything to make floating point as robust as possible.
They really did. It's a pretty amazing piece of engineering when you think about it.
So what other safeguards did they put in place?
Well, they also decided to tackle this concept of infinity.
Infinity? Wait a minute. We can actually store infinity as a value in our programs?
Yep. The IEEE 754 standard actually includes representations for both positive and negative infinity.
But isn't infinity just like this abstract mathematical idea?
It is abstract, but having this concrete representation for infinity actually lets us handle some tricky situations much more gracefully. Like imagine you're dividing a number by 0.
Yeah.
In some systems, that would just crash your program. But with the I standard, we can just return infinity as the result.
So instead of like a catastrophic meltdown, our program can just keep chugging along.
Exactly. It helps us handle those edge cases without everything falling apart.
That's pretty cool.
And it also lets us differentiate between different types of exceptional situations. Dividing by 0 is not the same as a calculation that just overflows the maximum value you can represent.
Right. Makes sense.
So having these different ways to represent those situations is really helpful. And then there's this other special quantity that's even more interesting, NaN.
NaN. What's that stand for?
It stands for not a number.
Not a number. Okay, that one sounds kind of philosophical.
It's basically a placeholder for results that are undefined or can't be represented as a number, like 0 divided by 0 or the square root of a negative number.
Yeah, those will definitely break math as we know it.
Right. So in those cases, the computer's basically saying, hey, I don't know what to do with this.
So it's like throwing up its hands and saying, I give up.
Pretty much. But the cool thing is that using NaN can actually prevent our programs from crashing when these weird undefined results pop up.
Oh, so it's like a safety valve.
Yeah, exactly. And it also lets us keep track of those undefined results as they propagate through our calculations. You don't want a NaN to just magically turn into some random number and then mess everything up later on.
So it's like a little red flag that travels along with the calculation.
Yep. A warning sign that says handle with care.
I like it. It's like the floating point equivalent of duct tape.
Haha, maybe. But here's another fun fact. The I standard even defines positive and negative 0.
Wait, positive and negative 0. Isn't 0 just 0?
Well, the standard actually defines comparisons so that positive and negative 0 are equal. But there are certain situations where the sign of 0 actually does matter.
Okay, now you have to give me an example. When does the sign of 0 actually make a difference?
Sure. So let's say you're calculating the reciprocal function, 1 divided by x.
Okay.
In some systems, calculating 1 divided by 0 would give you an error. But with signed zeros, you can actually distinguish between 1 divided by positive 0 and 1 divided by negative 0.
So it's like another way to preserve information and avoid those weird undefined results.
Exactly. It's all about making floating point behave as predictably as possible, even in those edge cases that most programmers never have to think about.
This deep dive has really opened my eyes to all the complexities of floating point. I feel like I have a much better understanding of how it works now.
Yeah, it's definitely one of those topics that's full of surprises.
And probably a few traps for unsuspecting programmers, too.
Absolutely. But the good news is that now you know what to look out for.
Exactly. Forewarned is forearmed, right?
Right. So next time you're writing code that deals with numbers, just remember all these little quirks and nuances we've talked about, and use the tools and techniques we discussed to write code that's accurate and reliable.
Well said. And on that note, we'll wrap up this deep dive into the fascinating world of floating-point arithmetic. We hope you've enjoyed the journey. And until next time, keep exploring those hidden depths of knowledge.